Alright, so welcome to this video. So Newton's method is not only used to find the roots of a function, but it's also used to find the x-coordinate of a turning point. In this case, you slightly have to tweak your formula just a little bit. So just a reminder, we all know that at the turning point, the first derivative is the one that is equals to 0. So more or less, what you then have to consider in your solution is that you have to perform a little bit of an alteration to Newton's formula, which is given to you. So because the derivative is the one that's going to equal to 0. So at the top here will be the derivative, and therefore at the bottom will just be the derivative of the first derivative, which is commonly known as the second derivative. So that is the only twist that you have to remember when using Newton's method now to determine the turning point. So let's dive right into it. So for us, what's quite important to remember, first of all, the interval that we'll be working with will be the midpoint of that, which is 1,5. But also more importantly, we need to find the derivative of this function, which in our case will be 5x to the 4 minus 3x squared minus 4. And then we have to find the second derivative. And therefore, for the second derivative, this becomes 20x to the 3 minus 6x. Another thing that's quite important to remember is that we know the turning point, the derivative is 0. But also, if you want to classify a turning point, we know that if the second derivative is positive, there will exist a local minimum. And if the second derivative is positive, there will exist a local maximum. So we'll use that in our last step in finding that particular equation. So let us dive right into it. So what we'll do now, if you want to find out what the first term is, we'll then substitute 1,5. But remember now, things are changing a little bit because we're finding a turning point. So this will have to substitute into the equation of the derivative. So this becomes 1,4 to the 4 minus 3 times 1,5 to the 2 minus 4. We're now going to divide that by the derivative, second derivative, which becomes 1,5 to the 3 minus 6 times 1,5. So what I will do, I'll perform this iteration on the calculator, and I will not show the steps, but it is important for you that you show all the steps until this actually converges. And that is the duty that you have with this question. So you ensure that you do that part. So let us see how we would do this on our calculator. So the way we would go about doing this on our calculator, I would start by going 1,5, pressing equals to so that I know that is now my ounce. So this becomes my ounce minus the fraction. Now I will have the first derivative there. So this will be ounce all the way to the power 4. This will become minus 3, put ounce in brackets, but this is now all squared, and this is going to be minus 4. I'll then go and put in the second derivative there. So this becomes my ounce all the way to the power 3, and this becomes minus 6. I plug in what my answer is. So I get that the first iteration that I get there, I'll get 1,2, I'll get 1,25, whatever that number is. And then what you then want to do, you want to continue with this process on and on and on until you get what the approximation value is that you get. So you'll go on. Okay, and you can see now as I press equals to, it does converge to this very number there. So now, because that it has hit that conversion, this means that this will be the x value of my turning point. So now you get back to the question that you're doing. So the way I've calculated this then just converges after about 5 iterations, and it starts giving me the same answer. And that same answer that you get there, you can plug it all into your calculator, and this will be the x value of the turning point. So you can plug this and get what the y value is of the turning point if you want, especially if you're asked to get the 2 coordinates. So you'll work out f of x of 5. So remember, you substitute that into the original equation. So I'll go x of 5 to the 5 minus x of 5 to the 3 minus 4 times x of 5. So you'll be able to perform a relative substitution and quickly work out what that is. And then what I do get from there, I get is minus 1 comma 1 minus 4 843. And then once you get that, that is actually what the coordinate of the turning point is, if you want to put it in that way. And then if we need to then determine the type of turning point that we get, I will then just plug the x value that I get, x of 5, into the second derivative. So this becomes the value that you get there, x of 5, which is like 1,150,77627. I'll plug that into the second derivative and check what kind of sign I get. And that will determine whether it's a local max or minimum. As I plug it into my calculator, this gives me approximately 21,39. So what this means about the coordinates of that turning point. So the turning point I was able to work out there is therefore a local minimum. So therefore you could say there now exists a local minimum at those coordinates of the turning point that you get. So the 1,150,77627 and negative 4,122,843 and so forth, we can say that this point will be a local minimum. And that's how we classify this. I hope this has made sense, and I hope that you've enjoyed this. So this does bring an end to our series on Newton's method.